Assalamu alaikum. Hello all. My name is Ibrahim Faris and today I'll be presenting our project Housing Price Classification utilizing a Level 2 MLOps pipeline. This project implements an end-to-end MLOps system for housing price classification focusing on automation, monitoring, and reliability. The system includes an automated CI/CD pipelines, real-time monitoring, stateless API serving, model versioning with MLflow, and a monitoring dashboard. Overall, this represents a mature MLOps Level 2 setup where manual steps are eliminated in the and the ML lifecycle is fully automated. System architecture overview. This slide shows the overall system architecture. The system contains of five uh, main components working together to create a robust production-ready ML pipeline. Each component is containerized using Docker, ensuring separation of concerns and scalability. This architecture enables smooth integration between training, deployment, monitoring, and orchestration workflows. So our main components are training pipeline that pre-processes the data, train models, and after that registers them to MLflow, prediction API, which serves the model using stateless serving architecture, a monitoring service to detect data drift and any degradation that could happen in our model, MLflow server as a model registry, and prefix server to manage the workflow executions, pipelines, and orchestration of the whole project. Our technology stack. This project uses industry standard MLOps technology stack. We are using scikit-learn for the model training, MLflow for model registry, Docker with 6 different containers, and CI/CD using GitHub Actions, orchestration using Prefect, Fast API as the API framework, and everything is hosted on AWS, specifically EC2. And lastly, the monitoring dashboard is built using Streamlit. Now I'm going to talk about the internals of our project. So firstly, with the model registry and orchestration. So we have MLflow that serves as a central hub for model governance. Every training run logs parameters, metrics, and artifacts. Automatically, models are registered using staging and production aliases. Whenever a new run happens, the model is given staging aliases, and then when it's promoted to production, it surely we're gonna give in production alias to enable safe promotion and rollback whenever it's needed. And this ensures full reproducibility and traceability of all ML assets. So here we have a simple screenshot of the ML flow. Secondly, we have Prefect that serves as a workflow orchestration. We have two pipelines. The first one is training pipeline that goes with whenever it's triggered, it's firstly pre-processes the given data, run the training of the model, and then registers the model to ML flow. And secondly, we have monitoring flow that will continuously checks for drifts and any model degradation. And whenever a severe drift is detected, it will automatically re-trigger the training pipeline. And this is a screenshot of the Prefect dashboard. After that, we have the containerization. We use Docker with 6 different containers. We have training container that manages the execution of the training, preprocessing, and model register to ML flow. And API container that from its name, it manages the API and serving of the model. The dashboard container, the ML flow server container, prefix server container, and monitoring container. This separation of concerns improves scalability, simplifies debugging, and ensures consistent deployment across environments. After that, we have the CI/CD pipeline implementation. Every code change triggers an automated formatting, type checking, and unit and integration tests. So whenever any pull request is made to the master branch, it checks for both code quality and testing. So there are two jobs in the CI, and whenever those two are passed, merge happens to the master branch, and the CD pipeline is triggered, and it starts by building the Docker images and then deploying those images to the EC2 and starts the near services. And after that, it does a health check to make sure everything is running correctly, specifically the API, and then it sends a phone notification just to inform us that the production is successful. So this is just a better developer experience using an app called Pushover. For advanced technical implementations, we have several advanced ML design patterns were implemented. We started by our dataset contains multiple high cardinality features such as addresses. So we handled those unique features, those unique values with hashing design patterns that caused the memory usage to be reduced by 74% while maintaining model performance. We went with hashing instead of embeddings because in addresses we have some overlapping between addresses that could be captured better by using hashing. Feature crosses, we captured some interactions that could affect the result. So we did district and heating and district and floor combinations that improved our model by 15%. Problem reframing, our dataset includes the target as the price in Turkish liras. We reframed that to a classification problem into three different buckets: low, medium, and high price. In simple methods, we used random forest, which is a bagging method with 100 estimators, and class weighting achieves 8% improvement over baseline. And then we have data rebalancing. We didn't need any data rebalancing since our dataset is almost balanced. Checkpointing, the model saves its state every 20 estimators. So in each training execution, it does that 5 times. So whenever an interruption happens, we have a point so we can resume our training. Stateless serving, we used APIs, specifically Fast API, which is a Python library. So we have two endpoints, a post endpoint to return the prediction and a health endpoint to check the health of the API. And it loads the model from the MLflow registry. And talking about that, we have algorithmic fallback. So whenever the API tries to fetch the model from MLflow, it has three tiers fallback strategy. So firstly, it tries to fetch the production model. If it fails, it tries to fetch the staging model. If it fails, it has a local file for any problems to ensure 99% service uptime. So we don't want any downtime. Stateless API, the prediction service is built using Fast API and follows stateless serving architecture. The API loads the model directly from the MLflow registry, as I said, and this design enables horizontal scaling, low latency under 100 milliseconds on average, and automatic request validation error handling. This is a screenshot from Postman showing how the request is happening. So we sent the data as JSON body, and we got our response. Monitoring and drift detection. Continuous monitoring ensures long-term model performance. We used PSI or Population Stability Index to detect the features drift, KL divergence to detect the prediction drift, and cardinality growth to detect the growth in cardinality in the prediction data. And each of those has a specific threshold. For example, we have for PSI 25%, and whenever a drift with a number larger than the threshold is detected, is going to generate an alert, and whenever we have more than 3 alerts or 3 or more alerts, is going to trigger the retraining to ensuring no degradation in the model performance. Monitoring dashboard. The monitoring dashboard provides a centralized view of the system health, visualizes performance trends, feature statistics, drift metrics, and record alerts, and it also allows to manual triggering of the pipelines. And this enables proactive issue detection and rapid response before performance degradation affects users. So if you have here some screenshots of the dashboard when drift was detected, and also we have alerts here. Model performance and results. The production model achieves strong performance and across all evaluation metrics like accuracy, F1 precision, etc. Operationally, we have reached deployment time for around between 1 and 2 minutes. Service uptime is 99%, 99.9%. The prediction latency is under 100 milliseconds on average, and automated retraining whenever drift is detected. And now I will go to the demo showcasing actually different parts of our project. So I'll start with the CI pipeline. So as I said, we have two jobs here, styling and testing. The styling is for formatting, linting, and type checking. The tests does the unit tests and integration tests, and this happens whenever a pull request is done to the master branch. And whenever any commit happens to master branch, we have the CD pipeline that build the Docker images, push to EC2, and checks the health of the API, and then sends notification on my phone. And this is for the CI/CD. After that, we have the prefect dashboard here. So this is the dashboard showing the different runs and like failed runs, successful runs. And I have two flows, two pipelines. The first one is the training pipeline. This is the final run. So it has three jobs: pre-processing, training, and then promoting the model. And for the monitoring flow, it just uh, records every feature validation, drifts, and plots. After that, in ML flow, so this is a example of a registered model here. So it registers the metrics like accuracy, F1, etc., and the parameters of the model, and like checkpoint intervals, estimators, and it surely logged the model artifact, and it uses versioning here. And if you went inside the model, we can see it gives the staging and production aliases to the model, ensuring correct alias is given to any new model. And for the dashboard, this is the monitoring dashboard. So this is overview of like total predictions in production, active alerts, the PSI or features drift, and the accuracy. We have some plots here, like how the distribution of different predictions from production service, and also it shows the flow status of prefects. We have different pages. We have drift monitoring to monitor the drifts of each, and feature statistics for each feature, each categorical feature here we have. And also, for example, we have a drift detected for the address feature, so we need to deal with this, but it's not a severe drift. Some performance metrics like accuracy, precision, recall, and here it shows the production data that is coming from the API. And lastly, we have the alerts. So we have only one alert, which is orange, so it's not severe alert, but we need to be careful about it. And also we have two buttons here, so we can trigger the training manually whenever we need to retrain our model. Lastly, I'm going to talk about the API. This is Postman. I'm calling the endpoint right here. I give it some data, and then when I send, I get the price category as medium. And this is for the demo. Achievements and key learnings. This project demonstrates the value of automated ML ops practices. The CI/CD pipelines reduce deployment time by around 94%. Continuous monitoring prevented silent model degradation. Stateless design and fallback mechanisms ensured high availability and no downtime. The key insight is that automation and monitoring are critical for ML machine learning systems at scale. And thank you for listening, guys. See you next time.